Hello, my name is Inês Silva, and today I'll be presenting the paper GUDIE, a flexible, user-defined method to extract subgraphs of interest from large networks. This project started with a problem that appears when exploring banking networks, which are usually large and highly connected. The question we got from our analysts is, how can we define the relevant context around a given user or card? So in this case, an entity such as a card will be connected to many others, such as other cards and merchants. And so if I wanted to know the transaction behavior of an entity in this banking network, which is the subgraph that would best represent it? Even though this started as a specific setting, this problem is very general. So the question is, given a large and highly connected network, how can we extract the relevant context around a given node? Answering this question will allow any investigator to easily explore the local graph information around that node. And the solution to this problem was GUDIE. So it is a new algorithm that extracts relevant context around a set of nodes in highly connected networks. The main innovation is that when computing these expansions, GUDIE takes into consideration both the network structure, but also user-defined criteria such as specific node or edge features. Another relevant property is that it is implemented as a message passing algorithm, and thus it is highly scalable to large networks. GUDIE receives a graph and a set of seed nodes, and then for each seed it will return the corresponding subgraph with the interesting expansion. The user-defined criteria can be given to GUDIE using two functions, a vertex interest function and an edge interest function. Now going into more detail about the algorithm, GUDIE has four main steps. First, node and edge interest scores are computed according to the interest functions provided by the user. Then we use the interest propagation step to compute the final interest score for each node. At each iteration, nodes message their neighbors their current score and then aggregate all the message received into a new score. And this process will run for a certain number of iterations, which is one of the parameters of GUDIE. Next, the seed expansion step uses those final interest scores and the seed nodes to compute the expansions. And here, nodes that are far away from the seed would be penalized using a decay function. Finally, we use a map-reduce operation to obtain the final subgraphs for each seed. To test GUDIE, we created 5 examples based on real banking networks. Here you have an example where we showcase that that GUDIE can ignore high degree and irrelevant nodes. And this feature would not happen if we were just using conductance-based expansions. However, if that node has a high interest, so in this case, for instance, we have a merchant that has a really high fraud rate, GUDIE will expand to that because it will have a high interest score. And GUDIE can also expand to high interesting areas through low interesting nodes. So even if you start in a low interesting area, you can find interesting areas around that low interest area through low interest nodes. As next steps, we can evaluate GUDIE in terms of scalability using real networks. We can perform user tests on analysts and even apply GUDIE to other domains. Thank you for your time, and I'm happy to answer any questions in the dedicated session.